In 1895, at the age of 16, Einstein's mind wandered what would happen if he would fly with a beam of light. If he would move at the same speed of light, would he see the light waves as frozen? Would he see himself in a mirror if he would carry a mirror with him? These questions accompanied Einstein during his university life, and after his graduation, until 1905 when he eventually solved it. Einstein's special theory of relativity. It is based on two postulates. 1. The laws of physics are the same for all observers in uniform motion. This postulate implies that the fundamental principles of physics, such as the laws of motion, electromagnetism, and gravity, are consistent and invariant for all observers who move with a constant velocity, relative to each other. In other words, there is no preferred or absolute reference frame in the universe. Whether you are making the experience while you are in a train, or traveling at a constant speed in a spaceship, or just standing on Earth making it in your laboratory, the outcomes of experiments and the behavior of physical phenomena will be the same. 2. The speed of light in a vacuum is constant for all observers, regardless of their motion relative to the light source. If the observer at rest measures the speed of light, it will be approximately 300 million meters per second. If this observer starts moving towards or away from the light source, at any velocity, the obvious way to calculate speed of light relative to the observer is to subtract the speed of light from the speed of the observer. But this is wrong, because speed of light will still as c, regardless of the observer's motion, so the speed of light is a universal constant. From these postulates, several key conclusions follow. 1. Time dilation. Time appears to pass differently for observers moving at different speeds. An object in motion experiences time at a slower rate compared to an observer at rest. This effect becomes more significant as the speed approaches the speed of light. 2. Length contraction. Lengths of objects appear shorter when they are moving at high speeds relative to an observer at rest. This phenomenon is also more pronounced as the speed approaches the speed of light. 3. Mass-energy equivalence. Einstein's famous equation, E equals mc squared, shows that mass and energy are interchangeable. It means that mass can be converted into energy and vice versa, as demonstrated in nuclear reactions and particle physics. 4. Simultaneity. Events that appear simultaneous to an observer at rest may not be simultaneous for an observer in motion. We know that events take place within a specific frame of time and space. However, when we approach speeds close to the speed of light, time changes. As a result, the new special frame experienced by a traveling observer differs. So, what this observer will see in his frame? There will be a difference between these two events, which the observer at rest watched them simultaneously. Albert Einstein's ideas transformed our view of the world today, alongside with other smart scientists, like Niels Bohr, Marie Curie, and Max Planck. Their works have made a revolution in our understanding of the universe.